Hi you guys, welcome to week 13. This week we're going to look at regression diagnostics, and I'm changing this a bit on the syllabus because I think this will be of more long-term use to you than covering some more on Bayesian statistics, and this is a good place to spend some time. So this week we have our RStudio assignment, although we're going to come back to RStudio just a little bit because there's a couple things I wanted to show you that Jamovi is not doing. If you have your assignment from last week, you can go ahead and just open that back up because we're going to use the stuff that we had from our multiple regression assignment from last week. If you don't have that, you can open that data file back up and run through to recreate the regression assignment, but you all should have that because you should have saved it. But if you need to, skim through that last video and run the analyses again. So here I am in our analyses, and your reading this week focused on what they call regression diagnostics, and we have looked briefly at some of our assumptions before, and we've been looking at these all semester, but there are some more in-depth things that we can look at and that people probably ought to know when conducting a regression analysis. So we're going to go ahead and look at that a little more closely. So on our output, we can go back to any of these analyses parts by clicking next to them. But we're going to go back to where we did the linear regression, and there's a couple things that I want to show you guys on here. So this week's readings focused a lot on residuals and some types of residuals, and it's probably the most detail-oriented stuff that we've done this semester. But I think it's worth committing some of those to memory when it comes to understanding regression, because it makes a difference on how much we can trust the results or our inferences that we're drawing from this analysis. So we talked a little bit about, in the reading, they talked about Cook's distance. And if you remember in the reading, especially the one for the learning statistics with Jamovi, he did a nice job of talking about our three types of residuals: our standard residuals, which are just, or our regular residuals, is probably the term that he used, which is just the difference between the predicted value and the observed value. The standardized residuals, the regular standard residuals, which take that value and divide by the estimated population standard deviation. And then a new one called a studentized residuals. And what that was they estimate a standard deviation, but they estimate the standard deviation when they delete that observation, and then they calculate that, and that's called a studentized residual. And in SPSS actually allows you to save those residuals and another and several other things, but another one that Field talks about in his text is the Mahalanobis distance for looking for multivariate outliers. And this is where Jamovi is showing its youth a little bit, in that we can't go and save any of those residuals back into our data set like you can with SPSS. In SPSS, there's an option in the regression menus to allow you to save those residuals in Mahalanobis distance, and they will appear in new columns on the data set, and have for each row they'll have the residual value for each of those types, and you can go look at them. And Jamovi just doesn't have that available yet, but they have some things to let us get by. And if you remember in the reading, he talked about outliers, which are points in regression that's a little more specific. In regression, the outlier is talking about a point that is far away from the prediction equation or from the regression line. And then he talked about high leverage observations, and those are ones that are significantly different than the other observations. And then he talked about high influence observations. And high leverage wasn't necessarily a problem, but if something is high leverage and it's an outlier, that is called a high influence observation. And that one is basically very influential in the direction and slope of the regression line or the regression equation. And the way we measure and look for high influence observations, which are outliers that have high leverage, is this number Cook's distance. And Jamovi does not put Cook's distance for each observation back into the data set for us, but they do give us this summary statistics table for Cook's distance. So we can see the mean for the Cook's distance for all the observations is 0.005. And the minimum value is 4.05 times e to the negative 7. So it's 7 decimal places down, which is very small. And the max is 0.07. And in the textbook, he gives us kind of a rule of thumb value of 1. If Cook's distance is equal to 1, then that data point may have an issue. And you'll see that 1 is definitely much farther above our minimum to maximum, so none of our data points are hitting that. I did a little extra reading on that, and 1 is kind of a very simple rule of thumb. And another thing to look at is if any of the values is a lot bigger than most of the others. And what I saw was kind of a line plot, kind of like a histogram, but it was a bar plot. And you could see all these little points down low, and then once in a while you'll see one that kind of jumps up much higher than the others. And it didn't get to 1, but there were a few points in the example that I was looking at online that did go higher than the others. So this solution from Jamovi is not perfect. It'd be nicer to see a plot or to actually have those values in our data set that we could sort them and look for any that were a lot higher than the others. But in our regression, we're okay. And this is, this kind of will tip you off if you need to go look at it further. If you do have a max that goes over 1, then you need to go look for it and look for those outliers. Even though Jamovi doesn't give us the numbers directly. Assumption checks. Another thing that it looked at was the variance inflation factor, or this VIF. And that's looking for multicollinearity. And this was looking to see if any of our predictor variables were too highly correlated with each other. And we did look at our basic correlations last week, and we knew there wasn't a problem. And not surprisingly, these VIF numbers are all pretty low. And the rule of thumb for VIF is a value of 10 or greater. If you have 10 or greater, then you probably have multicollinearity, and you better go make a choice about which variable you're going to keep in your analysis. This tolerance is actually the inverse, so it's 1 over the VIF. And so you'll see these are very close to each other, 1.01 and 0.986. If the VIF got up to about 10, this tolerance would be down to about 0.2. And so, you can look at whichever number you want, whether you're looking at the VIF and looking for 10 or above, or whether you're looking at the tolerance and looking for 0.2 or below. It's pretty much the same thing. They're just inverses of each other. And we don't have any problem with multicollinearity for any of our variables. And then the other assumption we were checking was the normality of our residuals. And here you can see this is looking at the standardized residuals, and we learned what those were. Those were the regular residuals that were divided by the estimated population standard deviation. So they have a standard deviation of 1, and you'll see that our residuals run pretty close to the normal distribution, and so we didn't have any real concerns. We also have a nice large data set, so we're not quite as concerned with that. And then we did talk about the residual plots. And here's the fitted with the residual. And with these residual plots, what you want to see is that the data points are pretty spread out evenly in the plots. So from on the x-axis from low to high, it looks like we have a good spread here. And on the y-axis from low to high, it looks like we're pretty much, we go from 0 down to -100. And, we got a point that's a little higher, but overall it looks pretty good. And then we have some residuals for each of our predictor variables. And you can see adverts here. It's a little more down towards the bottom than it is the top, and we did have some normality issues. We could go try a transformation if we wanted to. We're not going to worry about it. Airplay looks pretty darn good. Those are pretty even top to bottom and left to right. And image, that one is another one that we had some normality issues that we noted before. And you'll see this residuals plot. We definitely have a group over here, not much over here. And from top to bottom, we probably are a little heavier on the bottom than we are on the top. So that one, we could play with it if we wanted to, but we're not going to do that. So probably the place where Jamovi and our text on Jamovi was a little light was looking at some more individual diagnostics, and that's where Jamovi does not let us save anything to the data set. I did actually read, though, that that's kind of on their list of things to do that they're working on. So probably in a future release, we may see some more regression diagnostics. But I did, in field, he talks about this Mahalanobis distance. And Mahalanobis distance was kind of cool because it lets us see a multivariate outlier. It uses matrix algebra, and it looks at all of your predictive variables as a unit and calculates the distance of an individual observation on ththose 3 variables to, I believe they call it the centroid, where you can have several variables, and it calculates the middle in multidimensional space, and you get this number telling you how far your observation is from that centroid. And the bigger the number, the farther it is. And what makes it even a little bit more complicated is it's not just a single number cutoff, because it really depends on how many predictor variables that you're looking at. Maybe we can even look at, so I've got some notes in here in Jamovi, or in RStudio, and this bottom section here, So we'll put that into our, okay, there it is, I think. And it really depends what your cutoff is on how many predictors you have. And apparently, Mahalanobis distance is distributed with a chi-square distribution, and the degrees of freedom is the same as your number of predictors. And so we can see with 3 predictors like we have, we'd be looking at around 16. The online resource that I found for looking at Mahalanobis distance in R, and maybe we can just take a peek at that page. This is this upper link here. Somebody put a nice little tutorial for using, oops. Well, if my internet comes back up, then we will take a peek at that. But anyway, we can actually, I went ahead and translated that thing for you, and we'll run this block of code after we go look at this other. So there was another R site that went a little more in depth into regression diagnostics, and I went ahead and translated their code into how it would work on our system. And for this last part of this week's assignment, we're actually going to go back to RStudio. I tried pasting this code into Jamovi when I tried going to our editor, and you can give it a shot, but I actually got a bit of an error message when I tried to run these things. And so let's just give it a shot one more time and see if I don't get it this time. Now that I'm doing it for everybody, it probably worked just fine, but okay. So I don't know why when I paste stuff in here, several lines worth, that it gives me this error. When I try and run it one line at a time, it worked before. Go figure. Nothing's different. I don't know if I don't know why when I'm pasting several lines in. I don't know if it has something to do with carriage returns or formatting, something with that. But when I do one line at a time and I add another line in, it'll run it each time. But that would be very tedious, and we don't want to do that. So I went ahead and just put this back into RStudio. So if you want to, you can run this code. But before this, let's look at this. This is kind of a neat thing with Jamovi, and something I thought was kind of a nice idea, is there is a package called JMV Connect. And what that does is it allows R, and in our case RStudio, to talk to Jamovi so we can use the data set that we have open in Jamovi already and check it out. And so this very first step, this is the one that we used before for making sure we have the right packages installed. I took out our previous package list because we don't need all those for what we're going to do. But I do have my JMV Connect package, and I had previously installed this. So when I run, I get my little summary there. You may need to install it on yours. Hopefully you don't get an error. Some of you Mac people have been getting errors trying to install packages. Look for any pop-up windows behind your other windows. If it's asking for something, that's been something that's taken care of some people's errors, and some of them just needed to let it run for a while. But if you try running this a couple times, hopefully you should end up with this summary that JMV Connect is installed and running. So you can actually run things one line at a time by hitting Control-Enter. So if I'm on the line that I want to run, if I hit Control-Enter, you'll see that my one line ran. And this first command, this JMV Connect what, lets us see what data sets are available in Jamovi. And if I run that, and we go down below all this code here, you'll see that we have album sales, and that's the data set that we opened up. So then my next command right here, this read, lets us open up our data sales, and I'm just going to put it into a variable called data. So and then we're going to start getting into some plots and things, but you can actually run this whole section of code. So I have it in there. You can run the whole block, and you'll see RStudio went through and ran that, and we have a nice big selection of output that we can kind of click on and look at a little bit. And we'll just look at a couple of these. We're not going to go through it extensively. If you want to go through the other thing on diagnostics, it was a nice step-by-step tutorial of how to do this in R. I think the one command I will point out to you is this one. So this, and that's just a variable name, sales.lm, and I think they're standing for sales.linearModel. I can call that anything I want to, but this right here, lm parentheses sales tilde adverts plus airplay plus image, and then we're saying that data equals data, which is what we named our data set. If I'd named it Jack123, I'd say data equals Jack123, and it would know that all these variables are in that data frame. This is how you run a linear model or a regression model in R. And so I wanted you guys to see that, because this is how you do it if you were going to run this in RStudio. And then the rest of these commands are getting some of our information. So we're going to go look down at some of this. So that runs our model, but it doesn't really give us anything. But this summary will give us some of the output. And if we go and take a peek at that, so there was our, and you can just look at these, you're going to see what the output was. That was us importing the data. That was just a plot, a scatter matrix of our different variables with each other. And oh, looks like I walked over. Okay. So here is our linear model, and there's our model that we made. And here is some of the information for it. So we can have our coefficients. You'll see that it gives us our parts of the model first here. But if you look at these numbers and when compared them to the model that we did last semester, those numbers will match. And all of our predictor variables were significant. We saw that last week. And then we have our multiple R squared and our adjusted R squared. We saw that in tables. And we had our F statistic for our overall test, and 2 to the negative 16, which is very small. So we had a significant F test. And so we get pretty much all the same information, but it was sure a lot nicer to look at it in Jamovi, because those tables are a lot prettier than R puts it out. So I think this was a nice, Jamovi was a nice find for being able to have something a little nicer to look at and use. So some of the different plots, there's residual versus fitted. We saw that plot in Jamovi. There's our QQ plot that we saw in Jamovi. Jamovi has given us some stuff. And here we're talking about standardized residuals and fitted values, and that's nice and spread out. Residuals versus leverage. So that's something that Jamovi didn't give us. And there's actually a leverage amount that it is calculating for things. And I didn't quite figure out where this Cook's distance is. Oh, okay. So I think Cook's distance is this little red dashed line running way down there. So maybe. I'm not an expert in these plots, but those are some more plots looking at normality. Let's see what that one is. Square root of the standardized residuals and fitted. And in the tutorial, they go through some of these and talk about them. And these DF fits things had to do with deleting points out. So sometimes, if they delete a point out and rerun things, they'll see how big of a difference it makes. And I think these DF fits plots have to do with some of those. You can see there's a couple points out a little farther, but not a lot. Okay, Cook's distance. So this one is actually giving us a plot of Cook's distance, which is useful. And remember, we said that a rule of thumb was a value of 1, but you'll see that most of these are way down there at the bottom, but there are a couple points, particularly like these 3 up here, that they're a lot bigger than most of the rest of the others. So while they're definitely not reaching 1, they are bigger, and there's something a little bit more unique about these. So that plot's kind of useful, and it's a nice graphic representation of our Cook's distance. It'll be nice when Jamovi gets a little bit of that in there. So I wanted to just show you guys some of what R will do, and since we did jump into RStudio a little bit, there's no reason why we're limited by Jamovi. We can use RStudio very nicely with our Jamovi data, and DF beta, another thing, and let's see if there's another interesting plot in here. Hat values. And hat values, let me think for a second, those were values that looked at, see, and I just wrote the quiz and I'm already forgetting the hat values. But there are some points that have a higher hat value, and you're going to have to look it up in the reading because I am spacing at the moment. So okay, so this is a little more useful. We can see that some of these plots from some other packages gives us some of these points that may fall a little outside of some other ones. So there's a adverts and sales, and we can see which points might be a little outside of the normal of some of the others. airplane sales, and image and sales. And if we were having problems with our regression model, we would definitely be going through these plots and looking more closely at some of these 169, 164, 138, 169, 164, 169, 164. So those two are definitely outside of some of the other ranges that the other ones have been in there. So just something to look at. You can go through that, but I did want to show you Mahalanobis distance. So you'll definitely want to run that block before, because that's the one that loads the data into our data frame, so we can run this other block. But if you remember, we can click on the variable name and we can see our different data sets, and so we can go back to our tab and let's run our block for Mahalanobis distance. And this is the last thing I'm going to look at with you for regression diagnostics. So that ran, and what this is doing is it's calculating the Mahalanobis distance, and Mahalanobis was an Indian mathematician and he came up with this. And so there's the raw distance, and the next one rounds it off, and then we actually had it labeled as something an outlier or not. So I went ahead, when I looked up this example from the person that put that online, he used a cutoff of 20, which was a little higher than the chi-square would seem to indicate. So I went and changed it to 17 just to see if anything was above 17, and there were three things here. And if we want to sort those from top to bottom on the Mahalanobis distance, and we can see that our biggest value here was 18.6, and we can see the values that we had for adverts, airplay, and image. And I was just a little curious, like, did this particular observation come up in any of our previous things when we were looking just at univariate outliers? And I think it actually did. So when I looked at adverts and airplay back in our Jamovi file, those really weren't on the outliers, but we're going to go back and look at just on our univariate statistics. So if we went back up and looked at adverts on our box plot, the outliers that were on our box plot were all high, so that was not considered a univariate outlier. And same thing with airplay. The outlier was on the high end, not down on the lower end like it was on that data point. But our image score was 1. And this may look like we had 1 point, but actually that's just kind of an artifact of the way that a box plot is made. But Jamovi does give us one nice little option, and I'm just going to check it here, to let us actually see the data points superimposed on our box plot. And when this gets, and this thing called jittered means that even if points are exactly the same as each other, it's going to just shake them off a little bit so you can see where the data goes. And so you see our box plot with our whiskers, and there's our 2 outlier points. And you'll see there's 3 little points right down by that. And if we went back to our RStudio and looked at our image, we see we have our 3 values of 1, and then we have I'm going to go ahead and sort that. So we see we have 3 1s, a 2, a 3, and 3 4s. And those are the lower points for 4s. So if I went back to Jamovi, took a peek at that, we can see we have, there's our 3 1s, there's our 2, there's our 3, there's our 3 4s. So this jitter is kind of nice because it kind of lets you see where the data points would have fallen. And it'll be nice when Jamovi lets us put things back in the data set so we can look at individual points a little more. And this is one situation where having access to RStudio, would let us actually go look at individual data points a little more closely. If we were the ones collecting the data, we'd kind of want to make sure, did we get things right? But for your assignment for this week, I kind of shortened the questions. We're not going through the whole thing again. So how did our QQ plot look? It looked good. Did any of our residual plots have problems? And we did have one that was a little concerning, but you can go back and list that out. Were any of our VIF values problematic? No, there weren't any. What's the highest value for our Mahalanobis distance? That's going to be on our RStudio there, and you can just sort that, but I believe it's this 18.6 right there. Some model comparison stuff. So this is kind of the last thing. We'll go ahead and put this in here. So when we're doing regression models, sometimes we might have a couple different ways that we want to do a model. So when we did the simple regression last week, we just did adverts. And this week we've included airplay and image. And when I put all those variables into our covariates box, this is how it defaulted in Jamovi. But I can actually do a little more comparing on some different models. So I'm going to take those two out and I'm going to add a new block. And I'm going to put airplay in block 2. I'm going to add a new block, and you can see which one I'm working on by which one is highlighted here. I could go back to block 2 and change things. I can stay on block 3, and I'm going to put image in block 3. So what this does is now I'm actually looking at 3 different models. The first model just has adverts. The second model has adverts and airplay. And the third model has adverts, airplay, and image. And kind of my question is, well, which is the best model? Is it just adverts, or did these really make a difference that it made it a better model? And so now you'll see on our overall model test, we actually have 3 lines here, and that corresponds with our 3 versions of the model. And you can see our R and R squared, and R is actually going up quite a bit from one to the next. So from and since we're doing multiple variables, we'll go ahead and look at the adjusted R squared. And we can see that we're at 0.33, 0.62. I mean, that's quite a jump. That's like almost double what it was before. And then 0.66. So that went up a little bit. So we can tell that this second one definitely, is as much a predictor as the first one almost, and then the third one's coming in a distant third. And then you may wonder, well, how big of a jump is enough that it's significant? And luckily Jamovi does, and SPSS, if we were using it, does the significance test. And what this is doing is testing one model against the other. So this first one, this is testing a model with adverts in it compared to a model without any predictors in it. And as we saw when we did our simple regression, it was statistically significant, and it still is. When we add in airplay, so the model with adverts and airplay in it, how does that compare with the model with just adverts in it? And it is statistically significantly different. It is a better predictor. Our adjusted R squared is almost double. And then finally, when we add image in for a third model, how does that compare to the second model? And we can see that it is also statistically significant. So indeed, each model is successively better than the last one. If it's something that's not a good predictor, you would see that that f-test is not significant. And here's the model comparisons, which is giving us very similar information to what we had. But I do want to add in now another something here. These AIC, BIC, and RMSEA. And we'll give that a second to recalculate. And these are called information criterion, and they're kind of a way to compare models. We looked at one way with using our f-tests and our changes in r squared, and you can see that this gives us the change in r squared from 1 to 2 and from 2 to 3, so it calculates it for us. But you'll see these three new AIC, BIC, and RMSEA have appeared up here. AIC, we saw in the text, stands for Akagi Information Criterion, and that was developed by a mathematician called Akagi. And BIC stands for Bayesian Information Criterion. It's calculated under some slightly different assumptions. We're not going to go into it. And RMSEA stands for Root Mean Square Error. And these two, the Jamovi book didn't talk about, and we're not going to dig into the assumptions. But the thing to remember with all three of these, and they have some slightly different assumptions, but the smaller the number, the better the model. And so when you're comparing models, this is kind of a nice way to compare one model to the next. Besides looking at our significance tests, we can see which has the lower AIC, BIC, or RMSEA. And we can see that indeed, as we go from our first to our third model, that AIC number keeps getting progressively smaller. Same thing with the BIC. On all three of these, the lower number is better. There are other types of model comparison indicators that are not that way, but these three are. And you'll see that they all get smaller. So another way to tell that that third model is the best model. And I thought that's pretty neat, because that kind of gives us really something concrete to look at. And what's the best combination of predictors to predict some sort of phenomena? And then the rest of that is pretty much the same that we looked at. And there's our VIF. And the rest of that is stuff that we already looked at. So I hope you have a good week. And I will see you guys in office hours. So let's just double check. So what is the value for AIC for the final model? Which model is the best predictor according to the model comparison test? And we saw that that was number 3. And then the rest is the same. So now we can stop.